Right hand thumb rule. If a current carrying straight conductor is imagined to be held in the right hand such that the thumb points in direction of the current, then curled fingers of the hand indicate the direction of magnetic field. If current in conductor flows in the upward direction, then the magnetic field around the conductor is in anticlockwise direction. And if current in conductor flows in the downward direction, then the magnetic field around the conductor is in clockwise direction, as shown in this figure.
In this module, you will learn about an AC generator. An AC generator is an electric generator that converts mechanical energy to electrical energy in the form of an alternating EMF or alternating current. Working principle of an AC generator. An AC generator works on the principle of electromagnetic induction. In electromagnetic induction, when there is a relative motion between a coil and a magnetic field, an electric current or EMF is induced in the coil. Parts of an AC generator. An AC generator has an armature ABCD. It is a rectangular coil with many turns wound around a soft iron core. A shaft. It can be rotated rapidly. A field magnet. It may be a strong permanent magnet with concave poles. Two slip rings S1 and S2. These are connected to the armature and thus rotate with it. Two brushes B1 and B2. They provide electrical contact with the slip rings and a load, which may be a galvanometer as shown. Working of an AC generator. When the armature rotates between the poles of the field magnet, the magnetic flux linked with the armature changes continuously. As a result, an EMF is induced in the armature. This in turn produces an electric current through the armature and the galvanometer and through the slip rings and the brushes. Note that the galvanometer needle swings between the negative and positive values. This means that an alternating current is flowing through the galvanometer. Direction of induced current. Initially, the armature ABCD is vertical with its arm AB up and CD down. The direction of magnetic field is from left to right. As the armature undergoes a half rotation clockwise, arm AB moves down while arm CD moves up. According to Fleming's right-hand rule, the current will flow in the direction DCBA. So, the current will flow from B1 to B2 through the galvanometer. Now during the next half rotation, arm AB moves up while arm CD moves down. Again by Fleming's right-hand rule, current will flow in the direction ABCD, that is, from B2 to B1 through the galvanometer. Thus, the induced current changes its direction every half rotation. Graphical representation of induced EMF. Suppose the armature takes t seconds to complete one rotation clockwise. At time t is equal to 0 second, The armature ABCD is vertical with arm AB up and arm CD down. At this position, when the armature rotates, the rate of change of magnetic flux is momentarily zero. Hence, the induced EMF at this position is zero. During the first quarter rotation, the induced EMF increases. Then, at time t upon 4 seconds, the armature becomes horizontal. At this position, the rate of change of magnetic flux momentarily attains the maximum value. Therefore, the induced EMF at this position is maximum. During the second quarter rotation, the induced EMF decreases. Then, at time t upon 2, the armature again becomes vertical and therefore the induced EMF is zero. During the third quarter rotation, the induced EMF increases but has an opposite polarity as compared to that of the first half rotation. At time 3t upon 4 seconds, the induced EMF attains its maximum negative value. During the fourth quarter rotation, the induced EMF decreases and becomes zero momentarily at time t seconds as the armature is vertical once again. So the magnitude of the induced EMF is sinusoidal. In this module you have learned an AC generator is an electric generator that converts mechanical energy into electrical energy in the form of alternating EMF or alternating current. An AC generator is based on the principle of electromagnetic induction. An AC generator consists of an armature, a shaft, a field magnet, slip rings and brushes. The graph between the time and EMF generated by an AC generator is sinusoidal.
Approximately 5-6 remain
What exactly is the sandbox then?
It's a 3D metaverse. The building blocks are voxels, which are like 3D pixels. You can even animate. By adding and removing blocks, you can make any landscape.
I don't know how to.
Hello. Oh. Oh. Huh? Oh.
Once everything's perfectly organized, I'll start working on my thesis.
Grammarly will ensure you
Electromagnetic induction. In this lesson, we shall learn about electromagnetic induction. The phenomenon of electromagnetic induction can be demonstrated by an experiment. Wind an insulated copper wire on a paper or wooden cylinder so as to form a coil in the form of a solenoid. Connect the two ends of the coil to a galvanometer and place a magnet close to it. The reading of the galvanometer is 0 when the magnet is stationary. The pointer of the galvanometer deflects towards the right when the north pole of the magnet is moved towards the solenoid. The galvanometer shows 0 reading when the motion of the magnet stops. This proves that as long as the magnet keeps moving, current flows in the solenoid. If the magnet is moved away from the solenoid, current flows in opposite direction in the solenoid. Thus, the galvanometer deflects towards the left. The deflection increases if the magnet is moved away with greater velocity. If the polarity of the magnet is reversed and the magnet is brought close to the solenoid, then current flows in an opposite direction. The galvanometer accordingly turns towards the left. Faraday observed that current flows in the coil only when there is a relative motion between the coil and the magnet. The direction of deflection in the galvanometer is reversed if the direction of motion is reversed. The current in the coil and the corresponding deflection of the galvanometer can be increased by using a strong magnet or by increasing the motion of the magnet. Increasing the area or the number of turns also creates a strong current in the coil. According to Faraday, when there is no relative motion between the magnet and the coil, the magnetic flux within the coil remains constant. So the galvanometer shows no deflection. But when the magnet is moved towards the coil or vice versa, the magnetic flux changes and an EMF is induced in the coil. If the circuit is complete, the EMF causes current to flow through it. Based on his experiment, Faraday formulated two laws of electromagnetic induction. Whenever there is a change in the magnetic flux linked with a coil, an electromotive force is induced. The magnitude of the induced EMF is directly proportional to the rate of change of the magnetic flux linked with the coil. The direction of the induced EMF depends on whether there is an increase or decrease in the magnetic flux. John Ambrose Fleming gave two rules to determine the direction of motion, or the direction of induced current. While the left-hand rule is for electric motors, the right-hand rule is for generators. According to Fleming's right-hand rule, the thumb, forefinger, and middle finger of right hand are stretched perpendicular to each other. And if thumb represents the direction of movement of the conductor, forefinger represents the direction of the magnetic field, and the middle finger represents direction of the induced current. Lenz's law states that the direction of the induced EMF is such that it always tends to oppose the cause which produces it. Lenz's law obeys Newton's third law of motion, which states that to every action there is always an equal and opposite reaction. It also obeys the law of conservation of energy. It states that energy can neither be created nor destroyed. Therefore, the sum of all the energies in the system is a constant. Lenz's law is based on Faraday's law of induction. Lenz's law states that when an EMF is generated by a change in magnetic flux, according to Faraday's law, the polarity of the induced EMF is such that it produces a current whose magnetic field opposes the change which produces it.
Right hand thumb rule. If a current carrying straight conductor is imagined to be held in the right hand such that the thumb points in direction of the current, then curled fingers of the hand indicate the direction of magnetic field. If current in conductor flows in the upward direction, then the magnetic field around the conductor is in anticlockwise direction. And if current in conductor flows in the downward direction, then the magnetic field around the conductor is in clockwise direction, as shown in this figure.
In this module, you will learn about an AC generator. An AC generator is an electric generator that converts mechanical energy to electrical energy in the form of an alternating EMF or alternating current. Working principle of an AC generator. An AC generator works on the principle of electromagnetic induction. In electromagnetic induction, when there is a relative motion between a coil and a magnetic field, an electric current or EMF is induced in the coil. Parts of an AC generator. An AC generator has an armature ABCD. It is a rectangular coil with many turns wound around a soft iron core. A shaft. It can be rotated rapidly. A field magnet. It may be a strong permanent magnet with concave poles. Two slip rings S1 and S2. These are connected to the armature and thus rotate with it. Two brushes B1 and B2. They provide electrical contact with the slip rings and a load, which may be a galvanometer as shown. Working of an AC generator. When the armature rotates between the poles of the field magnet, the magnetic flux linked with the armature changes continuously. As a result, an EMF is induced in the armature. This in turn produces an electric current through the armature and the galvanometer, and through the slip rings and the brushes. Note that the galvanometer needle swings between the negative and positive values. This means that an alternating current is flowing through the galvanometer. Direction of induced current. Initially, the armature ABCD is vertical with its arm AB up and CD down. The direction of magnetic field is from left to right. As the armature
right
Working principle of DC motor. Working principle of DC motor is very simple. We can see that when the current conductor is placed in magnetic field, it experiences some force in particularly direction. The very basic construction of a DC motor contains a current-carrying armature, which is connected to the supply and through commutator segments and brushes. The armature is placed between north and south pole of a permanent or an electromagnet, in elementary model. One single turn of conductor is placed between two opposite poles. If we start to supply DC, via commutator system, current will start to flow. As we see, positive terminal of a battery is connected to left conductor of a turn, and negative terminal is connected to right conductor of a turn. As we see in model, north pole of the magnet is placed near left side, and south pole is placed near right side of the turn. Current in left side flows inward, and current in right side flows outward. As we see, conductor is carrying current and they placed in magnetic field. Both of them experienced mechanical force acted on them. Direction of mechanical force can be easily determined by applying Fleming's left-hand rule. To do this, spread out your left thumb, forefinger, and second finger so they are all at 90 degrees to one another. With that, if the forefinger is aligned along direction of magnetic field, from north pole to the south pole, and second finger is aligned along direction of the current and left side conductor, then thumb indicates direction of mechanical force. Similarly, if the forefinger is aligned along direction of magnetic field, from north pole to the south pole, and second finger is aligned along direction of the current and right side conductor, then thumb indicates direction of mechanical force. Due to this upward and downward forces on the turn, one torque is produced when turn rotates on clockwise direction as shown. After rotation of the turn comes to vertical position in respect of the magnetic field. At this position there is no current in conductor because turn, conductor and brushes rest between two commutators. Hence, there is no force acting on conductor, by due to moment of inertia, turn continue to rotates and comes horizontal again. Position of conductor has been changed here. That means conductor which was previously in left position comes to right position, and which was previously in right position comes to left position. At that position, we can determine mechanical force, with applying Fleming's left-hand rule. Let's do that. To do this, spread out your left thumb, forefinger, and second finger, so they are all at 90 degrees to one to another. So if forefinger is a line in direction of magnetic field, that is, from North Pole to South Pole, and second finger is aligned in direction of a current in a left side conductor, then thumb indicates direction of mechanical force. This is clearly upward here. So if forefinger is a line in direction of magnetic field, that is, from North Pole to South Pole, and second finger is aligned in direction of a current in the right side conductor, then thumb indicates direction of mechanical force. This is clearly downward here. Do this upward and downward forces, turn, tends to rotate in clockwise direction. From that explanation we can come to conclusion that, here in this model we can see that, whichever conductor comes near South Pole, experience upward mechanical force, and near North Pole, downward mechanical force. And do this continuously forces, mechanical turn rotate, even if battery is not connected. Particularly DC motor, rotates, at the same principle like this elementary model. Instead of single turn in DC motor we have mountain turns on major coil. And instead of 2 poles there is number of poles, installed. I hope that you like it. Please subscribe, like, and leave comment.
Electromagnetic induction. In this lesson, we shall learn about electromagnetic induction. The phenomenon of electromagnetic induction can be demonstrated by an experiment. Wind an insulated copper wire on a paper or wooden cylinder so as to form a coil in the form of a solenoid. Connect the two ends of the coil to a galvanometer and place a magnet close to it. The reading of the galvanometer is 0 when the magnet is stationary.
Now, we are going to discuss about working principle of DC motor. The working principle of DC motor is very simple. We know that when a current-carrying conductor is placed inside a magnetic field, it experiences mechanical force towards a particular direction. Let's take a simple elementary model of a DC motor. In this model, one single turn of conductor is placed between two opposite poles, that is North Pole and South Pole as shown here. Now, if we start supplying DC through a commutator system to the single turn, current starts flowing through it. At that position, as we see, the positive terminal of the battery is connected with left conductor of the turn and negative terminal of the battery is connected with right conductor of the turn. Moreover, we see here in the model, the south pole of the magnet is placed at left side and north pole of the is placed at right side. Current in this left side conductor flows inward and current in right side conductor of the turn flows outward. As we see, the conductors are carrying current and placed inside a magnetic field. Both of them experience mechanical force acting on them. The direction of the mechanical force can easily be determined by applying Fleming's left-hand rule. For that, we have to stretch forefinger, second finger, and thumb of our left hand at right angle to one another. With that, if the forefinger is aligned along the direction of magnetic field, that is from North Pole to South Pole, and second finger or middle finger is aligned along the direction of current in the left side conductor, then thumb indicates the direction of mechanical force. This is clearly upward here. Similarly, again, if forefinger is aligned along the direction of magnetic field, that is from North Pole to South Pole, and second finger or middle finger is aligned along the direction of current in the right side conductor, then thumb indicates the direction of mechanical force. This is clearly downward here. Due to these upward and downward forces on the turn, one torque is produced, which tends to rotate the turn in clockwise direction as shown. After clockwise rotation of 90 degrees, the turn comes to a vertical position in respect of the magnetic field. At that position, there is no current in the conductors of the turn, as the conductor end brushes rest in between two commutator segments. Hence, there is no force acting on the conductors, but due to moment of inertia, the turn continues to rotate and comes horizontal again. But position of the conductors has been interchanged here. That means the conductor which was previously at left position comes to right position, and which was previously at right position comes to left position. At that position, again mechanical force acts on the conductors, whose direction can again be determined by applying same Fleming's left hand rule. Let's do that. For that again, we have to stretch the forefinger, second finger and thumb of our left hand at right angle to one another. With that, if forefinger is aligned along the direction of magnetic field, that is from North Pole to South Pole, and second finger or middle finger is aligned along the direction of current in the left side conductor, then thumb indicates the direction of mechanical force. This is clearly upward here. Similarly, again if forefinger is aligned along the direction of magnetic field, that is from North Pole to South Pole, and second finger or middle finger is aligned along the direction of current in the right side conductor, then thumb indicates the direction of mechanical force. This is clearly downward here. Due to these upward and downward forces, the turn tends to rotate in clockwise direction as shown. Now from that explanation, we can come to the conclusion that here in this model, whichever conductor comes under South Pole experiences an upward mechanical force, and whichever conductor comes under North Pole experiences a downward mechanical force. And due to these two forces, the single turn continues to rotate until the battery is disconnected. A practical DC motor rotates with same principle as of this elementary single turn model. Practically, in a DC motor, in place of single turn, there is multi-turns armature coil, and in place of two poles, there may be more than two, even number of poles. Hope you understood. Thank you.
Motors are the most important elements of today's industrial world. From a simple drill machine to a sophisticated robotic arm, motors are used everywhere. There are two types of electric motors, AC motors and DC motors. In these, because of some important characteristics like fast reaction, better speed control, and simple construction, DC motors are very popular in automatic machines. In this video, we are going to understand the construction and working of a DC motor. Let us first start with the construction. The outer part of a DC motor, which is generally static, is known as stator. It consists of a frame and inward projected poles. Core of these poles are made from silicon steel, on which insulated copper wire is wound to make windings. These poles are bolted and fixed inside the frame. When DC current is passed through the windings, it creates static magnetic field. There are two sets of poles in a DC machine: main or field poles and interpoles. The connections of these poles are then brought outside through connectors in the terminal box so that we can give electric supply to them and even can do check for the fault. Main poles create static magnetic field when current is passed through its winding. In this magnetic field, rotating part of motor lies known as rotor or armature, made by number of stampings of highly permeable material, that is silicon steel, which allows magnetic field to pass through it easily. Slots are cut on the outer periphery of armature to receive coils of copper conductors. Each coil gets connected to an external DC source by a pair of commutator segments arranged in form of a ring. This complete assembly is housed over a cylindrical shaft made up of high quality steel. Because of the bearings at both sides of the shaft, the rotor is capable to rotate between the field poles. When electric current is forced to pass through the rotor conductors by a set of carbon brushes through commutator segments, it creates their own magnetic field, which tries to distort the magnetic field created by the field pole. Due to interaction between two magnetic fields, electromagnetic forces act on the rotor conductors, and these forces act tangentially on the rotor surface. Therefore, a torque is produced at the rotor shaft and the rotor rotates. To understand this process more easily, let's take an example of a single loop having a set of its own commutator segment. Due to the DC voltage applied by an external DC source, current will flow in the coil in this direction from positive to negative potential. And by Fleming left-hand rule, we can find that this side of coil receives force in upward direction and this side will receive a downward force, and hence the loop rotates. During the rotation of loop, we can find that commutator segments comes in contact with brushes of opposite polarity one by one. This way, the conductor of left side always carry current in this direction and of right side in opposite direction. This helps to maintain continuous rotation of the coil. We can also find that magnitude of force on the coil is maximum in this region. After that, magnitude reduced considerably. This causes uneven torque and movement of rotor. To make maximum torque always available at the shaft of rotor, more such sets of coil with a pair of commutator segments are placed in the rotor. When one coil passes through the region of maximum torque, next coil will take its place. This way, shaft of rotor always provide higher and smooth torque. Coils are connected to the commutator segment in such a way that every instant of time, each and every coil carries current, but the sides of coil who comes at the left hand side carries current in one direction, and the sides at right hand carries in opposite direction, irrespective of the rotor position. This can be achieved by the lap or wave connection of windings. We will discuss about this in our upcoming videos. To ensure that the current given to the commutator segments will not reach to the shaft, mica insulation is placed between them. In a small DC motor, permanent magnets can be used to create static magnetic field. But they can lose its magnetism due to heating, vibration or aging. That's why in high rating motor, electromagnets are used. and their magnetic field density can be controlled to control output torque. Let's have a look at the coil design. If a singleton coil of thick wire is used here, then it allows higher current and give higher torque. Whereas if multi-turn coil of thin wire is used, then current and torque is also reduced, but we get higher speed. That means at the time of manufacturing, we can decide whether we want high torque low speed machine or low torque high speed machine. Here, the work of interpole is to reduce sparking at the brushes over commutator ring due to the effect of armature reaction. Again, we will discuss its detail in our upcoming videos. To energize the field poles, we can use same DC source which runs our DC motor, or we can use a separate source. The method which we use will decide the type of DC motor. In our next video, we will see different types of DC motor. At last, all the connections from armature to the field poles are brought outside in the terminal box, and covers are fitted from both sides of the motor. So this is about the construction and working of DC motor. Hope you like the video. If yes, please like and share it. Dear friends, if you haven't subscribed our channel yet, please subscribe and also press the bell icon. Then only you will get notification of our upcoming videos. Thank you.
Hi, hope you have seen this transformer. Sometimes it could be a small or big size. A transformer is a passive electrical device that transfers electrical voltage levels from one circuit to another through the process of electromagnetic induction. It is mostly used to increase the voltage levels between circuits, which are called step-up, or decrease the voltage, which is called step-down transformer. Today, this video going to explain the working function of the transformer. Let's start with the main parts of the transformer. The core is the main part, and it is called the heart of the transformer. The core is made up of iron, or silicon steel, or ferromagnetic materials. It is thin metal strips and lamination insulated by a coat of varnishes or papers. The core of the three-phase transformer consists of three limbs in the same plane, and each limb carries both low voltage, LV, winding, and high voltage, HV, winding. The core provides a magnetic path flux around the core. The first winding is also known as a coil. When it is supplied by an alternating electrical source, the alternating current through the winding produces a continually changing and alternating flux surrounding it. If another winding is brought close to the first winding, some portion of this alternating flux will link with the second winding. As this flux is continually changing the amplitude and direction, there must be a changing flux linkage in the secondary winding or coil. According to Faraday's law of electromagnetic induction, there will be an EMF induced in the second winding. If the circuit of this secondary winding is closed, then a current will flow through it. This is the basic working principle of a transformer. The winding which receives electrical power from the source is known as the primary winding. The winding which gives the desired output voltage, due to mutual induction, is commonly known as the secondary winding. Here, if the number of secondary coil turns is greater than the number of turns primary coils N1, then it is called a step-up transformer. That means increasing voltage between the primary to secondary windings. Conversely, a transformer that decreases voltage between the primary to secondary windings is a step-down transformer. The alternating current through the primary winding of each phase produces a continually changing magnetic field that surrounds the winding. Here this magnetic field is linked with the secondary winding by magnetic flux, which flows through the transformer core. EMF will be produced at the secondary winding based on Faraday's law. And this induced EMF is defined as mutually developed EMF. Insulation is needed between the primary and secondary winding to prevent short circuits. Finally, to receive electric energy from the transformer, insulated bushings are needed. During its working, or transferring the power from the primary to the secondary winding, various energy losses happen. Like eddies current losses, hysteresis losses, and copper losses. All these losses generated heat. To prevent heat, transformer oil is used inside the tank. The main role of transformer oil is to act as a coolant and to insulate. Transformer oil is an exceptional heat conductor, and can effectively reduce the copper coil's temperature, stopping them from burning. Not only that, externally cooling tubes or radiators are there. The radiator of the transformer accelerates the cooling rate, thus it plays a key role to increase the loading capacity of an electrical transformer. A Buchholz relay is used to detach any fault inside the transformer. Hope you understand the working function of the transformer. Thank you. Let's grow up. Never stop learning.